So today the task is to examine all three of these definitions of what it means for a function to be continuous at a point, not in their affirmative but in their negative version. To look at each of these three functions and decide why, based on each of these three definitions, those functions are not continuous at x equals 0. And you'll notice that each one of them is defined in sort of this weird piecewise fashion. And any time in a calculus class when there's a piecewise thing showing up, usually your antenna goes up and says, oh, there's some funny behavior, right? There's a lack of continuity or lack of differentiability or some property that we like to take for granted in calculus. Oftentimes, writing down a piecewise function is the only way to make them not happen. So let's take a quick look at the graphs of f, g, and h, and then we'll come back to these definitions and how they may or may not be satisfied. So first of all, the f of x function, which is x squared everywhere except at x equals 0, and is equal to 3 at x equals 0. Did anybody, when you took calculus, have a name for this kind of discontinuity? Did you call it something special? Sometimes calculus authors do, sometimes they don't. What's one way of... I don't know. There's actually a couple different first letters that could be. Yeah, this is an example of a discontinuity that's called a removable discontinuity. And what's removable about it? Where does it get that name? What do you think? Removable discontinuity is called that because you can make one happen by removing one point, a single point, out of the graph of a continuous function. So if I just take the function f of x y equals, the graph y equals x squared, and I just delete one point from it, and then maybe reassign that point somewhere else so that this function still has the domain all real numbers, right? So we're not breaking the domain up. Then this continuity was created by removing a point. Conversely, we could also think of it as a removable discontinuity because we can remove the discontinuity by just filling that point back in. Right? If I just move that single point up at 0, 3, if I just move it back down to the origin instead, now what I get is, again, the graph of a continuous function. So removable discontinuities, in a sense, are the easiest ones to repair. Right? If we had liberty to change the function, we would only have to change it at a single point. We would only have to change that value at a single point to make it continuous again. So that's an example of what we often call a removable discontinuity. That's our f of x. I actually want to look at h of x next. This is the Heaviside step function. And this, I think, is what I would call an example of a jump discontinuity, something we heard about before. Jump discontinuity. And unlike, what's the big difference here between this discontinuity and the removable discontinuity that we looked at a moment ago? The fact that this graph is not continuous, the fact that this function is not continuous at x equals 0, is not just a feature of the value at x equals 0. It's a feature of an entire whole half of the graph in this case, right? One whole half of this graph doesn't match up with a whole other half. In order to repair this discontinuity, it's not enough for me to just take one point and move it. I would have to somehow take an entire collection of points. In order to fix this discontinuity, I would have to do something like kind of connect up the dots like that, right? And that requires me not just patching up a single point, but actually patching up a whole bunch of different points if I wanted to fix up this discontinuity. So jump discontinuity is somehow profoundly more discontinuous, quote unquote, than the removable discontinuities. I'd say the most enigmatic discontinuity that we can look at in a class like this one is the one that arises in this function, sine of 1 over x. And then there's an attempt at x equals 0 to fill in the value x equals 0. So what's going on here? Why can we not say that this function is continuous at x equals 0? Let's think for a moment about the limit definition. If this function were continuous, actually this was g, so if g of x were continuous at x equals 0, then what would have to be true according to the limit definition? What would the limit of g of x as x approaches 0 have to be? If this function were continuous at x equals 0, then the limit as x tended to 0 of this function would have to be 0, but that's not because 0 is somehow special here. It's because we have forced 0 to equal g of 0. Right? Remember, this is the limit definition of continuous. Limit definition of continuous says that the limit as we approach a value of x needs to be the same thing as the value of the function at that value of x. The nearby values have to agree with the at value of this function. And so since we have, in our piecewise function, forced g of 0 to be 0, we would need for this to be true. And so if we were to analyze this function for continuity, we would have to justify why this statement is not true. And it could be not true for a couple different reasons. It could be not true because g of 0 doesn't exist, right? But we specifically forced it to exist in the piecewise function. And so here, there's now two different reasons why it could not happen. This limit could exist but be different from 0, or this limit could just not exist at all. And it turns out that that's the version that is true here. It turns out that the limit as x tends to 0 of this function, sine of 1 over x, does not exist. But it's a little bit subtle to see why. If we take a moment, if we just look at the graph for a moment and zoom in on it, and zoom in a little further, zoom in a little further, zoom in a little further, what is sine of 1 over x actually doing as x tends to 0? So it's still doing what a sine function does, right? It oscillates between +1 and -1. But the closer we get to x equals 0, what's happening to the wavelength of those oscillations? It's getting smaller and smaller and smaller and smaller. So this function is oscillating faster and faster, and in fact the graphing tool has trouble even depicting just how quickly this is happening. Once we get far enough in, like in the twilight zone. So this function, what sometimes I like to call it, oscillates itself to death near x equals 0. It doesn't actually settle in on a value as x tends to 0 because it continues to oscillate. And however close to 0 we try to get, the function will always oscillate itself out of any epsilon strip around 0 if that strip is sufficiently small. So we can, it turns out, make the argument that it's not continuous because that limit just doesn't exist. But that's a trickier one to work with than the f of x and the h of x that I'd like for you all to work on for the rest of our class today. So the task, again, is going to be to take either f of x or h of x, depending on which group that you are working in today. Demonstrate, first using the limit definition, that it's not a continuous function at x equals 0. And then also choose one of the other two definitions. For today, that choice is free, so whichever one you want to use. And show why it also does not meet that other equivalent definition of continuity for the point x equals 0.